We'll do quite a bit of integration in this class, and the particular process we'll use may be a bit unfamiliar to you. So let me do an example to get you started. Let's let v equal dr dt, where v is 4 square root of t plus 2. We're asked to find an expression for r of t if r equals 0 when t equals 0. Start by substituting the expression for v into equation 1. This gives us 4 square root of t plus 2 equals dr dt. We're going to have to integrate to find an expression for r, but to do that, we need to separate the variables. This just means that we need to rearrange the equation to get all of the r terms on one side of the equal sign and all of the t terms on the other. And now we can integrate. In this class, we will always use definite integrals, and we will need to pay close attention to the limits of integration. In particular, the limits of integration need to match the differential or d term. For example, on the left side of this equation, the differential term is dr, and the limits of integration should be values of r. Similarly, on the right side, the differential term is dt, and the limits of integration are values of t. Moreover, in this class, the lower limits should be the initial conditions of the system. The upper limits should be the variables we're integrating. This will give us an expression that holds for any time t after the initial conditions. Now we can integrate and evaluate the expression at the limits of integration. Simplifying gives us the correct expression for r of t. I need to spend a short time on some new notation. In dynamics, we often put a dot above a variable to indicate a derivative with respect to time t. For example, x dot equals dx dt, y dot equals dy dt, z dot equals dz dt, and so on. Similarly, two dots indicate the second derivative of a variable with respect to time. In dynamics, we also use the chain rule and the product rule quite a bit. Let's do an example using the chain rule first. Let's say that y equals kx squared minus x, where k is a constant and x is a function of time. What is y dot? Well, y dot is dy dt, which is the derivative of kx squared minus x with respect to time. How do we take this derivative? You might be tempted to say that it is 2kx minus 1. The problem with this is that 2kx minus 1 is actually dy dx rather than dy dt. So that isn't quite right. Instead, we need to apply the chain rule. The chain rule says that dy dt equals dy dx times dx dt. Now we can plug in the expression for y and take the derivative with respect to x. Just remember to keep that dx dt term. And now remember that dx dt equals x dot, and this is the correct answer. Here's another example. Let's say y equals k cosine 2t, where k is a constant. Now what is y dot? Y dot is still dy dt, which is the derivative of k times cosine 2t with respect to time. Once again, you might be tempted to say that y dot is k times negative sine 2t. The problem with that, and this is going to seem a little weird, is that that answer is actually the derivative of y with respect to 2t. If it helps, think of the angle 2t as x. So we were actually taking the derivative of y with respect to x instead of t. The good news is that the chain rule will give us the right answer. So let's start again. Y dot equals dy dt, and I'm going to apply the chain rule replacing x with 2t. Now we plug in the expression for y, which is k cosine 2t, then take the derivative of the cosine with respect to 2t, which is negative sine 2t, and remember to keep that d2t dt term. Then the derivative of 2t with respect to t is just 2. Simplifying, we get a final answer of negative 2k sine 2t. Okay, What if we wanted to find y double dot? Well, we just do the same thing again. Y double dot is dy dot dt, and I'm going to apply the chain rule again and plug in the expression for y dot that we just found. The derivative of that expression with respect to time is negative 2k times cosine 2t. The derivative of 2t with respect to time is just 2, and the final answer simplifies to negative 4k cosine 2t. Let's do another one. Let's say that x is k cosine 2 theta, where k is a constant but theta is a function of time. What is x dot? X dot is dx dt, but it might help to apply an expanded version of the chain rule here, where we'll take the derivative of x with respect to the angle 2 theta, then take the derivative of the angle with respect to theta, then take the derivative of theta with respect to time. Then we can plug in the expression for x, which is k cosine 2 theta, and now we can take the derivatives. For the first term, we have our constant k and the derivative of cosine 2 theta, which is negative sine 2 theta. Then d2 theta d theta is 2, and d theta dt is theta dot. The whole expression simplifies to negative 2k theta dot sine 2 theta. Okay, so what is x double dot? It's the time derivative of the expression we just found. Now we need to be extra careful here. We need to take the time derivative of two functions of time that are multiplied together. For this, we need to use the product rule. We start by taking the derivative of the first expression, circled in orange, and multiply it by the second expression, circled in purple. Then we take the first expression and multiply it by the derivative of the second. Again, we remember to apply the chain rule, and simplification gives this longer expression. Hopefully the chain rule and the product rule are all review, but if you have trouble remembering them, Appendix C in the textbook can help.